they were no longer alone. A new class of creatures was evolving independently alongside them that would take flight to new heights.
Convergent evolution is a phenomenon where organisms from two different ancestries evolve similar characteristics in response to similar environmental pressures. And the evolution of flight is an excellent example of convergent evolution. Birds and pterosaurs both evolve similar body plans in response to the need to fly more efficiently.
From pigeon to peacock, eagle to sparrow, today there are over 10,000 species of birds on the planet, twice as many as mammals. Exactly when they evolved and how they adapted flight is a 230-million-year-old detective story. But if you know where to look, there are telltale clues.
Hey, how's it going?
Ironically, the answer to how birds took to the air may lie on the ground. Large flightless birds like emus help trace the origin of avian flight because it is believed that birds evolved not from winged pterosaurs, but ground-dwelling dinosaurs.
This animal, the emu, is one of the closest things left on Earth that might be able to tell us what non-avian dinosaurs really looked and acted like. For instance, look at the feet of an emu. You see scales on the feet like a reptile, and also 3 weight-bearing toes like a non-avian theropod dinosaur.
Theropod dinosaurs stood upright, with hind legs used for support and movement, while short forelimbs were used for grasping and tearing prey. The most famous was the fearsome T-Rex.
If we were to look at the foot of a T-Rex and put a T-Rex foot next to the foot of this emu, you'd see many, many similarities and only a few differences. I think the most obvious feature that birds share with non-avian dinosaurs, a feature they inherited from non-avian dinosaurs, is their feathers.
Feathers were long thought to be exclusive to birds among vertebrate animals, but this was not the case. Millions of years ago, some non-flying vertebrates had feathers too.
So we now know that feathers are not unique to birds. Feathers first evolved in non-avian dinosaurs, and it's quite possible they evolved for something other than flight. Possibly insulation, possibly brooding their nests.
But aside from sharing feathers, how do we know that birds evolved from dinosaurs? And how were these land-based animals able to take to the skies? Over the last 200 years, paleontologists have begun to find amazing evidence that helps to answer these evolutionary mysteries in the form of incredibly preserved fossils. Pittsburgh's Carnegie Museum of Natural History houses one of the world's top collections of dinosaur bones. Among them are striking clues of how birds and subsequently bird flight evolved from dinosaurs.
This is a cast of Archaeopteryx. And when this was discovered well over a century ago, it astounded scientists because the fossil shows a mixture of features classically associated with reptiles and classically associated with birds.
Archaeopteryx was the first of a whole new group of animals. It was a bird, distinguished from a feathered dinosaur by its ability to fly. Even though it may not have been very proficient in the air, there were clear differences in the anatomical structure of this creature compared to non-flying dinosaurs. As the world's oldest known bird, however, it naturally had not completely evolved away from its ancestors.
Archaeopteryx, when we look at its skeleton, it shows many features that are retained from its dinosaur ancestors that are lost in modern birds. So for instance, if we look at the skull of Archaeopteryx, we see that it retains tiny teeth. All known birds alive today lack teeth. We also see a long, bony tail in Archaeopteryx, a dinosaurian feature. If we look at the hand of Archaeopteryx, we can see that its fingers are still tipped with large, curved claws, and this is a feature that dinosaurs have as well.
In addition, Archaeopteryx also seemed to be missing something else crucial: muscles. Modern birds have a series of large pectoral muscles that attach to their sternum and help them generate enough force to fly. Archaeopteryx didn't appear to have these muscles. So while their bodies could support some flight, it is unlikely they could stay airborne for very long periods of time.
Archaeopteryx probably could fly, but compared to modern birds was almost certainly very clumsy. We know this because its skeleton is much more primitive than that of modern birds.
So how did modern birds evolve to become more efficient flyers? What was the next evolutionary step after Archaeopteryx? In 2004, on a dig in northwestern China, Lamanna and his colleagues came across another fossilized piece to the puzzle.
The more I looked, it became clear that we were looking at a very bizarre group of birds that were abundant during the Cretaceous period, the final period of the age of dinosaurs.
Close to 100 nearly complete skeletons of 100-million-year-old birds were recovered on the dig. Among them, a rare specimen. Tiny fragments of this long-extinct animal, called Ganzis, had been found before, but never a skeleton as complete as this one.
Ganzis dates to 40 million years younger than Archaeopteryx, about 110 million years ago. And already, relatively rapidly in bird evolutionary history, Ganzis has acquired many of the features that we associate with modern birds. It's in many ways an anatomically modern bird from 110 million years ago.
Although Archaeopteryx was capable of flight, Lamanna would soon discover that Ganzis had anatomical features that almost certainly made it a far better flyer.
A lot of the story of the evolutionary history of birds has to do with the increased efficiency of flight. So for instance, when we look at Archaeopteryx, we see features that are not present in modern birds, such as teeth and a long bony tail. And these are two features that have long been argued to have been lost in modern birds because they saved weight.
Loss of teeth, a shorter tail, and other distinguishing features appears to make Ganzis an intermediate animal between the largely dinosaurian Archaeopteryx on one side and modern birds on the other. But did the fossil have the pectoral muscles that could help it get airborne more easily than Archaeopteryx? Trouble was, although the Ganzis fossil was complete, it was also badly flattened, making it nearly impossible to see the certain anatomical features of this new species. Would critical questions to this mystery go unanswered? Fortunately, Lamanna is able to turn to a team of paleosculptors and artists at the Carnegie Museum of Natural History to try and recreate the image of this ancient bird. Working like crime scene investigators, the team is able to methodically reconstruct the crushed bones and create a picture of what Ganzis would have looked like. As Lamanna had hoped, Ganzis appeared to have a body capable of supporting large, strong wings. The presence of a bony sternum on Ganzis means that this creature would have most likely had larger pectoral muscles, compared to the relatively puny ones seen on Archaeopteryx. Today, all flying birds have large muscles, similar to those found in Ganzis. This provides them with the strength needed to flap their wings and get airborne. Could Ganzis have been the evolutionary step to allowing birds to become more proficient flyers?
This guy would have had pretty big pecs, you know, been able to flap his arms with quite a bit of force and probably was a pretty good flyer.
The large breastbone that strong flight muscles could attach to is clearly seen in Ganzis, as well as fused wrist and hand bones, a short bony tail, and fused ankle and foot bones, also traits in most modern birds. All these features transformed these early flyers from a reptile that could get airborne to a radical new lineage that would spend the majority of its time in the air.
Ganzis was probably an excellent flyer, probably as good a flyer as are many types of modern birds.
Birds are one of the most successful groups of vertebrates, but in order to survive in a new environment, major anatomical changes had to be made. What was useful on the ground would hold them back in the sky.
When birds gained the ability to fly from dinosaurs, it came with some costs. They had to lose a few things. The most obvious of which is probably that they don't have any more hands.
All the bones of the fingers are now incorporated in the wing, and there are feathers attached to them, so they can no longer manipulate anything with their hands or defend themselves on the ground. Regardless of this cost, however, the fossil record clearly shows that the evolutionary transition from dinosaurs to birds was a great triumph, and over time, birds radiate far and wide.
These
These groups that evolved the ability to fly and diversified into hundreds or thousands of species have gone on to fill many different niches in the environment.
Incredible fossils like Archaeopteryx and Ganzis help us to understand what anatomical features define a bird and when they evolved. But what were the environmental factors that send birds into the air?
When we're trying to examine the origin of flight, of bird flight, we need to answer a couple of questions, and perhaps the biggest one is, what were the selective forces driving birds into the air?
What was happening down on the ground that turned two-footed feathered dinosaurs into masters of the skies? Through the fossil record, we know that birds that were capable of flight evolved from dinosaurs over 140 million years ago. But the biggest mystery of all still remains. What forces would have driven land-based creatures to take to the skies?
When somebody asks what was the behavior of a fossil, of course, we're reaching in to an area of speculation, to say the least. How do we explain each of the transitional stages from the bird's dinosaur history to today?
Ken Dial, professor of biology at the University of Montana, thinks the answer of how flight first evolved lies not in the bones of long-dead animals, but in the behavioral patterns of those that are living.
What we're trying to do is we're trying to borrow from the present to try to interpret the potential behaviors of the fossil creatures.
Dial and his colleague Brandon Jackson run an avian flight research center in the foothills of Montana. Their work focuses on uncovering the origins of bird flight.
Why do birds need to fly? Why do they want to fly?
Dial believes that birds evolved the power to fly slowly. Over time, environmental pressures like escaping predators pushed them towards the sky, and various physical adaptations allowed them to get there. If this is true, claims Dial, many birds may still be hardwired with the behavior of their land-dwelling ancestors inside. In other words, if given the choice between using their wings or their feet, birds will choose to remain on the ground. To test their hypothesis, Dial and Jackson put birds in a position to have to choose between flying and keeping their feet earthbound. They take birds that are fully able to fly and place them at the foot of a ramp with a steep incline.
Here we go.